Hello everybody and welcome to Psych 301 Lab, where in this review we're going to be talking about regression. If you haven't already, I'd suggest you go back and watch the video I posted that accompanies this one that talks about correlation. As you'll see, regression is a very natural extension of that correlation concept. And also I'd urge you to go watch Dr. Siegel's lecture from Thursday, which covers both of these topics together in one lecture. So without further delay, let's go ahead and dive right in. And I'd like to start by reviewing the concept of correlation graphically using this scatter plot here. So we're going to be talking about correlation, which is built on this idea of a statistical relationship between two variables. That is, how changes in one variable are reflected in changes in another variable, or broadly, how two variables, quote, co-vary together. And for this review, we're going to be looking at this variable that I'm going to denote with x, and that's going to refer to exercise, and this variable that I'm going to denote with y that refers to well-being. So each participant in our sample then is going to have some score related to how much they exercise and another score related to their overall well-being. I'll remind you that on the scatter plot, each participant is reflected as a point on this plot, and that point is meant to show where their two scores on x and y intersect. So if I were to have a point, say, here, that point shows this person's score on x, so where that falls on the x-axis here, and where it intersects with their score on y, which is represented on this y-axis here. So if we were to do this for our whole sample, we'd end up with this scatter plot that kind of has this cloud shape of some kind. Let's say it looks something like this. And I can look at this scatter point and make a few conclusions already about this statistical relationship. So we talked broadly about a statistical relationship having three main facets to it. The first of which is form. So if I look at this scatter cloud, I can see that its form is what we would describe as linear, because all of those dots follow a trajectory. In other words, this scatter cloud does not have any curves or bends or S-shapes or anything like that. I can see where the trajectory is relatively straight the entire time. So I know it's of linear form. Once I know that the form is linear, I'm able to then talk about the strength of this relationship. And we talked about quantifying the strength of a statistical relationship using our Pearson's product moment correlation, or our Pearson's R statistic, which we calculated as that covariance term standardized by dividing it by the product of each variable's standard deviations. Once I know the strength of the relationship, and I can also just see this visually, we could also talk about the third facet, which is the direction of the relationship. And here, I can see that this is a positive relationship. And I can tell it's a positive relationship because as scores on x increase or move down that x-axis, scores on y also increase or move up on the y-axis here. So I know that this is a positive statistical relationship, and I can measure its strength by calculating Pearson's R. So that's kind of our quick gist of a correlation. When we talk about regression, there's going to be a little bit of nuance to this concept, but to start off, we want to think about how we can represent or summarize this data cloud. And in our review of correlation, we talked kind of vaguely about this idea of fitting a line through this scatter cloud here. We referred to this line as the line of best fits, but it might be more aptly called in our context the regression line. And so today in our review of regression, our main focus is going to be on this line, how we obtain this line, and what this line actually does for us. And it turns out it's going to be very much based on prediction. This line represents our best summary of this scatter plot, or in other words, it represents the best summary of the relationship between these two variables. We can think of this by analogy, kind of like how a sample mean is the best representation of our samples data, which consists of many different scores in whatever sample we might have. So my best guess for any one person's score in my sample of a single variable situation is whatever my sample mean is. That is my best guess. Here, we're going to use this regression line in kind of a similar way, where my best guess for anyone's score on one variable can be formulated on the basis of scores on the other variable. And if that sounds a little bit vague at the moment, that's okay. We'll flesh this out as we go through this presentation here. So let's go ahead and get started with our review of regression then. So the way I see it is that regression has three key areas that we need to focus on. And all presentations are different, so this is by no means exhaustive. And this is just kind of my take. So first, we want to understand the idea of prediction and modeling, because this is very unique to a regression context that we don't really talk about as much with correlation, even though they're very related to one another. Second, we want to understand the regression model itself, and that regression model is based on getting that line I just showed you. So we want to talk about what the parameters are and what those parameters mean. And then we also want to talk about how to calculate those parameters, because calculating those parameters is going to help us get that regression line. And finally, we want to understand how to test the regression model, and we do so by assessing what we would call model fit. And we can assess model fit in a few different ways. What we're going to see is that we have a way of assessing it using a hypothesis test. Namely, we're actually going to use ANOVA or an F test to evaluate model fit. And we could also assess it using an effect size, which we're going to refer to as R squared, where the variance explained in one variable as a result of the other variable. So these are our three key points that we're going to cover in this review today. So on the first point, prediction and modeling, regression is about prediction, and our aim is to predict scores on one variable based on the scores of one or more other variables. Now the scores that we're going to predict are going to be scores on what we're going to refer to as the dependent variable, or some might call this the response variable. That's just a little bit of different language in the regression context. And we're going to predict the scores on this dependent variable based on the scores of one or more independent variables, or what we might call our predictor variables, or our predictors. I put these S's in parentheses because we don't necessarily have to have more than one predictor, and in everything we talk about in this class, we're just going to deal with one predictor, but it's conceivable that we could have more than one. So in our example of correlation just a moment ago, I treated exercise as the independent variable and well-being as the dependent variable. And so in that example, that regression line represented the prediction of scores on well-being based on the scores of exercise. So this leads us to a central question in the regression concept, and that is, can the predictor variable or variables be used to explain the variance in the response variable, of which we only have one? Well, we actually have a way to quantify that variance explained, and that's going to be quantified using this R squared statistic, which is really just the squared value of our correlation if we're dealing with just one variable, or what we called the squared multiple correlation if we're dealing with multiple predictor variables. And again, we're going to keep it simple and just focus on one here. But yeah, this sounds a lot like correlation. And that's because, broadly speaking, regression can be thought of as a way of just summarizing one or more correlations on the predictor variables and how they relate to the response variable. We're going to be predicting these response variable scores based on all of those predictor variable scores. So on modeling in particular, and what we mean by modeling, a model is something we construct and impose on the data. And I really want to emphasize those terms, construct and impose on the data. The data will be there no matter what, but we choose to conduct a regression on it, and we build that regression model based on some sort of theory, at least in ideal terms we would. The point is here is you conduct your study and you obtain measurements for your predictor and your response variables. So here, exercise and well-being. Those scores or those measurements will be there no matter what you do. And you can build all sorts of models based on those scores. Or even more nuanced, if I have multiple predictor variables, let's say I have exercise, maybe how often someone practices like some mindfulness activity like meditation, or a host of other variables, maybe their income, all these other things. I choose which of those predictors to put into a regression model. I choose how that well-being dependent variable might be predicted on the basis of whatever predictor variables I want to use. The data is there regardless, and we choose to see how this model fits that data. Emphasis on that word, fits that data. We can theoretically construct all sorts of different models on the same data. And in fact, it's even plausible that all sorts of different models might fit the data well, might be, sensible relative to that data. So it's really important here that we emphasize that we build these models based on theory as well, and that these things are fallible depending on whether we're justified in building that model in the first place. So these types of analyses where we're building modeling, where we're trying to predict things, very much are dependent on what we as researchers decide. So it's based on our human decisions as opposed to just kind of the agnosticism that might come with just thinking about the math of it all. So we decide, how to evaluate our model fit. We decide what goes into our model and things like that. So to close out our first point here, or our first key area of regression is about prediction. So we're going to be trying to predict the scores on one variable based on another, the scores on our dependent or response variable based on the scores of our independent or predictor variable. And we're building this model hopefully with some sort of theoretical backing. So with that said, let's go ahead and move on to the regression model itself. So for the regression model, our main question here is how do we predict y scores from x scores? And we're going to denote our predicted y scores using this y hat you can see here in parentheses. So anytime we guess or estimate a y score for a person, it's going to be that person's y hat, or if you hear me use that term, that's what I'm referring to. Well, the way that we predict these scores is we're going to use that line of best fit, again, probably better referred to in our terms as our regression line. And what we haven't let on up until this point is that this regression line here actually plots each person's x score against their predicted y score. So this line here actually is made up of all these predicted y scores. So I'll do a quick example for you. Say for this person here, let me highlight them. Let's say for this person here, we have their x score. However, on the basis of our model, we predicted that their y score should be here, wherever that x score intersects the line. So we have what we might refer to as a little bit of error right here in that prediction. But this person is going to have an x score, they're going to have a y score, and then they're going to have a predicted y score. And so this line here, this regression line, is just going to be made up of everybody's predicted y scores going forward. And so the question then is, how do we determine this line of best fit? Or what criteria do we use to determine this line of best fit? Well, the criteria we want to use is something called minimizing the residual sum of squares. And when we make reference to the residual, we're making reference to this error right here. We want to minimize the amount of error in our prediction, so it's a relatively straightforward idea. But let's talk about this a little bit more in depth. So, how do we determine which line is best? And we answered that already. We want to minimize what we call the residual sum of squares, which is the error in our prediction. So we know what a sum of squares term is by now in relation to our sample variance. And this is something we actually reviewed in the last video when we talked about correlation. Well, here in the regression context, we have what we call our sum of squares residual. And that sum of squares residual is calculated like this. We take the sum of each person's actual score on Y minus the score that our model predicts for them on Y, so Y hat, and we take its square root. We square that deviation, and then we sum across everyone in our sample. So if we look back, that would be, again, that blue error. Anywhere we see a difference between someone's actual Y score and their predicted Y score, that's going to be represented mathematically by this deviation here. And then we're going to sum all those deviations after we square them. So the sum of squared deviations for the residual, or you might even refer to it if you want as the sum of squared error, if you like. And the idea is that we want this total here, this sum, to be the lowest it possibly can be. So in total, we want the least amount of squared difference between each person's actual Y and the Y that we predict with our regression model. And again, this might seem really strange because you might be asking yourself, okay, why are we predicting all these Y scores when we actually have a person's Y score in the first place? And again, I would clarify that possible confusion by again thinking back to the idea of a sample mean. Why are we calculating a sample mean for a group of people when we know all their X scores? Because it's the best representation of them as a group. It's the best representation of these two variables, exercise and well-being, broadly. And in fact, we can even tie the sum of squared residual and the idea that we want to minimize that sum of squared residual. I'm seeing that I spelled this wrong. Minimize the sum of squared residual in the same way that our sample mean minimizes our general sum of squares term. So I'm not sure if I covered this in depth in 301, but I know it's something we talk about in Psych 210. And I'll just ask you to remember that the sample mean minimizes our regular, I can't spell that word, minimizes our regular sum of squares. So our sum of squares is usually equal to the sum of each score minus something squared. And I can put anything in that blank space. I can put any number with relation to that X, but what we find is that if we were to put the sample mean in that blank spot, whatever that equation comes out to is going to be the lowest possible solution we could possibly get. So if I put a number larger than the sample mean, take all the deviations from the X scores and square them from that number and total that, it'll be something greater than if I put the sample mean there. Likewise, if I put some number smaller than the sample mean in that blank, take all of the x scores minus that number squared and total them, I'll also get something larger than if I just put the sample mean here. So by definition, our sample mean minimizes the sum of squared deviations. Likewise here, the sum of squared residuals, or the criteria by which we're going to find the best possible line, is the one that minimizes the sum of squares term. And if you really are struggling with this concept, you maybe bring it down to the kind of simplest explanation. We want the line that just minimizes the amount of error in our prediction. And this equation here is how we quantify that error in our prediction. We don't want our predicted y-scores to be wildly different than the y-scores we already have. More difference equals more error. So we want to minimize that amount of error. So now let's talk about how we actually calculate this regression line. If you remember way back from high school math or maybe some college algebra or geometry, I'm not sure where this is taught, but you might remember the equation for a line. Just a regular line, and you might have learned this with different terminology, but I learned it as such. Y equals mx plus b, where this m is our slope, this b is our y-intercept, and this x is just some x-coordinate or score or something to that effect. Well, now I want to show you what the equation for a regression line looks like and draw some comparisons to these two things. So our regression line equation looks like this. We say that for a given person, their score on y that we predict, so y hat, is equal to this beta subscript 0 parameter plus this beta subscript 1 parameter times some score on x for that person, plus some bit of error. Now, we're not going to really focus much on this error term here, so let's kind of just set that out of our minds for now. There will be error in our prediction, of course, but we're going to quantify that using the sum of squared residual like I just talked about. But look how much these two equations resemble each other. Now, the regression line equation uses these parameter notations and is in a different order, but it's largely the same here. This b, or y-intercept for the regular equation for a line, well, this b subscript 0 is the same thing. That b subscript 0 parameter is our y-intercept parameter. This m here for our slope, well, that's represented by this b subscript 1 parameter. And then we also have x represented too, where we multiply that x value by that slope. So our parameters here are very much similar. And I'll go ahead and just write them out for good measure here. We have our predicted y-score for an individual. And we're going to calculate that predicted y-score on the basis of some y-intercept parameter plus some slope parameter times that individual's score on the predictor variable. So we would estimate someone's well-being score or predict someone's well-being score on the basis of some y-intercept parameter, some slope parameter, and that person's exercise score. If we're going to follow the same type of mentality that the same type of example that we were using before. This error term, I'll mention, this EI, I said that we quantify this using the sum of squared residuals, and that's because this error term for a given person is just going to be that person's actual y-score minus their predicted y. But practically speaking, we're not going to use this error term in any calculation steps because we can assess it later. So when looking at a regular line, let me draw some axes here. We saw that if we had something like, I don't know, y equals 2x plus 1, that our y-intercept is going to fall on 1 on that y-axis, and that our slope is going to be up 2 over 1. Up 2 over 1. And we get some type of line, that looks like this, that'll run through those points. For a regression line, it's going to look largely the same, except this regression line is going to come on a scatter plot. And I'll also note, when we talked about this in early algebra in grade school or early university courses, that this type of regular line didn't really build in any error. So it's kind of like a perfect situation, or maybe we're just learning about it in the terms of like coordinate geometry, so it's just a little bit different. When we talk about a regression line, however, this is going to represent our statistical relationship between two variables. So it's going to operate, as we kind of alluded to earlier in this presentation, on a scatter plot. So here we're going to have all of our different people represented as points once again. And based on what we calculate for our intercept and our slope, we're going to produce this line, where here, whatever value that y-intercept is our slope parameter. That's going to be the same for each and every person. Whatever value we calculate here as our y-intercept parameter, that's going to be the same for each and every person. Whatever rise over run rate, or whatever we calculate for our slope, is going to be our slope parameter, and that's also going to be the same for every person. And the only thing that differs in how we calculate all of these predicted y's is going to be each and every person's score on x. And then again, we also have that error between each person's x score and that predicted y score. That would be like error for that person. So let's go ahead and break down how we actually calculate these parameters, and therefore how we obtain this regression line. So to calculate each person's predicted y-score, as I just mentioned, we need to calculate a slope parameter and an intercept parameter that's going to be used in each and every person's calculation. And this equation here is the calculation we use for each and every person. And we're going to do this in a very specific order. First, we're going to calculate the slope. So that's first. Second, we're going to calculate the intercept. And third, we're going to plug in that slope and intercept term for each and every person, and that's how we're going to get each and every person's y-hat. Now, in reality, we don't actually have to do this math. It'll be done in R or whatever statistical software, but this is what's going on behind the scenes. So we're going to take these things in turn. So we're going to start with calculating the slope. Parameter. So to calculate the slope parameter, we're going to use the following equation. Our slope parameter is going to be equal to the sum of each person's score minus the mean on x, or a predictor variable, times each person's score on y minus the mean on y, or the response variable, and we're going to divide that numerator by the sum of each person's score on x minus the mean on x squared. And so at first glance, this equation might look a little bit new to you, but hopefully the component parts of this equation are a little bit more familiar. For example, in this numerator here, we described this in the last review of correlation as our sum of cross products. And as it happens, this is also that numerator for the covariance that we standardized to calculate our Pearson's correlation. If you remember, the covariance had that in the numerator, and then we just divided by n minus 1. So this is the same numerator as our covariance. This bottom piece here in our denominator, well, that's just our sum of squares for the x variable. So if we were to calculate, for example, the sample variance or the sample standard deviation for that x variable, this would be the numerator of that variance term. So while the slope parameter itself is a new equation, the pieces that comprise that equation should be a little bit more familiar. And I'll also mention that if you wanted to, let me get rid of this covariance here. If you wanted to, you could also calculate the slope parameter in a different way. If you already calculated the Pearson's R correlation, then this slope parameter is also equal to that correlation times the standard deviation for the response variable divided by the standard deviation for the predictor variable. This equation is equivalent to the one above that uses the sum of cross products and the sum of squares for x, or the predictor. So that's our first step, is to calculate that slope. Our second step is going to be to calculate that intercept. And calculating the intercept is even more straightforward than calculating the slope. And in fact, the reason we have to do this in a specific order is because we need that slope parameter to calculate that intercept term. So here's the equation to calculate that intercept. Our intercept term is equal to the mean for the dependent or response variable, so the mean for y, minus that slope we just calculated times the mean for the predictor variable or independent variable, or the mean for x. This here is our intercept, and it's super simple to calculate this once we have that slope parameter. So we calculate our intercept then, and finally, all we have to do is plug and play for each predicted y. So for calculating our predicted y-scores or y-hats, just like the equation I showed you a moment ago, we're going to plug in that intercept parameter plus that slope parameter we calculated in the previous two steps, and we're just going to multiply it for each person by whatever their score on x is. And that's going to get us all these predicted y's, and then for each and every person, we're going to have a pair of coordinates. We're going to have their actual x score, and we're going to have their predicted y score. And those coordinates right there are what is going to give us that regression line. And so it's super simple to get these predicted y's once we have those two intercept and slope parameters. And in fact, if we just calculate two predicted y's for two different individuals, if we were doing this by hand, then we can just connect those 2 points and get the whole line in one foul swoop that way. So now that we have the calculations in place to get that regression line, we still have to evaluate whether our regression model is actually a good fit to the data. So we're going to go ahead and turn now to our final key area for this review, and that's going to be model fit, where our main question is, how do we test whether our model is a good reflection of the data, or again, how that model fits the data? Does our model reflect the picture that that data presents? And I want you to remember, of course, the caveat that we can fit all sorts of models to that data, and we can even fit all sorts of good fitting models to that data. So we need to have some theoretical backing as to why we choose the model that we do. We don't want to just rely on these data-driven approaches where we just fit a model, and if it fits well, we start to make theoretical conclusions based on that alone. So our main question here, how do we assess model fit? Well, the first way we're going to look at this is going to be hypothesis testing. And more specifically, it's going to be hypothesis testing via an F-test or via ANOVA. So what I want you to do is remember back to a couple weeks and remember how our ANOVA sum of squares breaks down. So remember ANOVA where our sum of squares total could be partitioned into two parts where we had that sum of squares between and that sum of squares within. So sum of squares total was equal to sum of squares between plus sum of squares within. And from that, we calculated an F statistic. That F statistic looks something like this. We had the between variance in the numerator. We divided by the within variance in the denominator, and to do so in actual statistical terms, we had the mean square between divided by the mean square within. That mean square between was just the sum of squared between divided by the degrees of freedom, so it's really just a variance calculation. And the same for the mean squares within, the sum of squares within divided by the degrees of freedom within to get that variance term for the within variance or for the within effects. So we're going to use this same principle in this regression context where we're going to take our sum of squares total for the regression model, and we're going to break this into two component parts. We're going to call it the sum of squares regression, which is kind of analogous to the sum of squares between, and the sum of squares residual that we talked about earlier. Or if you like, you can think of this as the sum of squares for the regression model and the sum of squares relative to error. So let me draw that out on this new slide. We have the sum of squares total equal to the sum of squares regression plus the sum of squares residual. And that's going to produce for us, once we obtain those degrees of freedom as well, the same type of testing format as just a one-way ANOVA, where we have an F statistic. That F statistic is going to be a ratio of variability of the model variance to the error variance. And that's going to be reflected by two terms, variance terms, that mean squared for the regression divided by that mean squared for the residual, where each of these mean squares is calculated using a sum of squares term divided by a degrees of freedom term. So again, this F statistic is a ratio of variability between the model and the error variance, and so it's pretty intuitive to kind of wrap your head around what drives that F statistic up and makes it more likely that we reject the null hypothesis. So in this context, we want, if we hope that our model is significant, we want to reject that null hypothesis. In other words, we want our F statistic to be significant. So the more variability that our model explains, or the better our model predicts why, the higher that F statistic is going to get. Conversely, the more error variance we have, the larger that denominator is going to get, and it's going to drive down that F statistic. So it's the balance of these two things, this ratio of variability, that's going to affect whether we reject that null hypothesis or not. And simply, again, if this is still kind of vague to you, you can really wrap your head around it by just thinking that we want to minimize this error variance. The least amount of error in our prediction is going to give us a higher F statistic and a better fitting model. So we want to make sure that our prediction is as accurate as possible. So I'll just rewrite this equation here. We have our sum of squares total. Let me do that in the correct color. Sum of squares total equal to the sum of squares for our regression model, which I'll just call sum of squares reg, plus the sum of squared residual for the error in our prediction. So our total sum of squares, I'll mention that this is all with respect to the dependent variable y, or response variable. So our total sum of squares is going to be the same sum of squares term that we would use to calculate the sample variance for that y variable. So it's going to look something like this. It's going to be the sum of each score on y for each person minus the mean on y squared. So that's the same thing we would use in the numerator of a sample variance. Well, whatever we get for that total sums of squares is going to be equal to the sum of squares regression. And to calculate the sum of squares regression, we take the sum of each person's predicted y score on the basis of our model minus the mean on that variable squared. That's our sum of squared regression, plus our sum of squared residual, which we've actually already mentioned a few times. This is the error in the prediction, and this is equal to the sum of each person's actual score on y minus their predicted score on y squared. If you recall from that scatter plot, that was the deviation between each person's actual scatter point and the regression line. And remember that we have to go through and solve that regression line equation for each person to do this, but in reality, R is going to do this in the background for us. So we have our sums of squares terms. Now we need our degrees of freedom terms, and we use those degrees of freedom terms with the sum of squared terms to get those mean squared terms we need for the actual F ratio. Okay, so for these degrees of freedom, we have our degrees of freedom total that is also partitioned out into two component pieces, our degrees of freedom regression and our degrees of freedom residual. Our degrees of freedom total is going to be the same as it always has been. It's going to be the sample size minus 1. For our degrees of freedom regression, this is simply going to be equal to k, where k is equal to the number of predictor variables. In this case, we just have 1. We have that x variable, or exercise in our running example. And then our degrees of freedom residual is going to be n minus k minus 1. So as we have more predictors, that degrees of freedom residual is going to change. But in this example, let's say we had a sample size of 30. Our degrees of freedom total would be 29. If we only had one predictor variable, then the degrees of freedom regression would be 1. And if we had, again, only one predictor variable, our degrees of freedom residual would be 30 minus 1 minus 1, or 28. So those are all the parts that we need to get those mean squares terms, which we can use for our F ratio. So once we do so, we can get a mean square for our regression, which again is equal to the sum of squares for our regression divided by degrees of freedom for our regression. That's going to be equal to the sum of each person's predicted y score minus the mean y squared over k. And we can get the mean square residual equal to the sum of square residual divided by the degrees of freedom residual. That's going to be equal to the sum of each person's actual score on y minus their predicted score on y squared over n minus k minus 1. And finally, that's going to leave us with our F statistic, which is going to be that mean square regression over that mean square residual. So that's our first route of assessing model fit. And again, if our model fits the data well, we would expect to reject this null hypothesis. In other words, that F statistic should get larger the better our data fits the model, or excuse me, the better our model fits the data. But we can also look at this in terms of an effect size too. So if we want to assess model fit, we could also do so using this effect size method. We should actually do these in conjunction with one another. But this effect size is going to be that R squared. And this R squared calculation is going to be the sum of squares regression divided by the sum of squares total. In other words, it's the ratio of the total variability that is explained by our regression model. So as you can imagine, the larger our sum of squares regression is, the larger this R squared value is going to be, or the more variance that our model can account for without any error, the larger this R squared is going to be. And we have a pretty straightforward interpretation for what this R squared value is, or what it means, and it means the following. It's the amount of variance in our dependent variable y explained by x, or if we have multiple predictors, explained by the whole set of predictors together. So if we have an R squared calculation of 0.78, that in turn means that 78% of the variance in y is predicted or explained by x, which would be a really high R squared value. All right, so for some final notes here, I just have a quick statement to make that you can see in the lecture slides. I believe it's like slide 35 here. And we're not going to go through these tests in great detail, but they are something you'll see in R, so you'll also see them in the lab scripts that we go through together. And that's this. We also test the significance of the intercept parameter and the slope parameter separately using t-tests. And so we can, in fact, test whether a predictor that we use is actually a significant predictor of whatever our response or dependent variable is. And this is especially important if you think about having a multiple set of predictors. So let's say we predicted well-being based off of your amount of exercise, your income, and your, let's just call it something broad like mindfulness practice measurement. It might be the case that the whole regression model is significant, but maybe only your maybe only your exercise score and your mindfulness activity scores, maybe those are the only variables that are actually significant predictors of your well-being. Maybe income is not significant, and we can evaluate that predictor by predictor using those t-tests. So that's not something we're going to flesh out here in this review or in the slides. We're not going to do the math for these things. But just know that that's some important output to interpret, and we'll see that a little bit more closely when we actually go through the lab script together soon. So without anything else, that's the end of our regression review. As always, feel free to email me with any questions or concerns you might have, and I hope you all are doing well this week, and we'll catch you in the lab script review as well. Bye.